Usually, programming a computer it's kind of a master and servant dynamic.
Right.
You write a line of code, and the machine just executes that line. You give it this really rigid sequence of steps, and it follows them blindly, to the letter.
Yeah, that's the standard paradigm.
But there is a programming language that flips this relationship entirely. You don't tell the machine what to do step by step. You just tell it what is true, and you let it figure out the rest.
Which is a huge mental shift.
Oh, absolutely. So today, for you, the learner listening right now, we are diving into a stack of sources detailing a language that has been quietly powering artificial intelligence and complex databases for, well, over 50 years. We're unpacking Prolog.
It's quite a legacy.
It really is. And whether you are a seasoned software engineer or just someone fascinated by how machines think, this deep dive into our sources is going to challenge your most basic assumptions about problem solving. Okay, let's unpack this.
To truly grasp what Prolog represents, you really have to look at it as a bridge.
A bridge.
Yeah. On one side, there is formal human logic, like the way philosophers and mathematicians describe the world using relations, variables, absolute truths.
Right, like formal proofs.
Exactly. And then on the other side, you have cold, hard machine execution. Prolog was designed to be the infrastructure connecting those two worlds. It allows a user to compute complex answers by simply querying a set of logical relations.
The sources show this language didn't just emerge in a vacuum, though. It was essentially born into a philosophical battleground in the 1970s.
Oh, yeah, it was highly contested.
The story starts around 1972 at the University of Aix-Marseille in France. Two researchers, Alain Colmerauer and Philippe Roussel, developed this new system. And the name itself is basically a dead giveaway to its purpose.
Right, it's an abbreviation for the French programmation en logique.
Programming in logic.
Exactly, and the academic foundations beneath it were pretty dense. The language was built on Robert Kowalski's procedural interpretation of what are known as horn clauses.
Okay, horn clauses, that sounds intense.
It's jargon, but to strip that away, a horn clause is essentially a specific, highly restricted type of logical formula. Think of it as a strict if-then structure.
Like, if this happens, then that happens.
Sort of. It allows you to say, if condition A and condition B are met, then conclusion C is definitively true. And the motivation here was deeply practical.
How so?
Well, these researchers wanted to reconcile two competing ideas in computer science. On one hand, using pure logic as a declarative way to represent knowledge, and on the other, the procedural step-by-step representation of knowledge that was, dominating North America at the time.
And that tension brings us to what the sources describe as the transatlantic rivalry. Reading through the historical context, the computer science world was practically split in two.
It really was.
European AI researchers fiercely championed Prolog, while American AI researchers were firmly entrenched in a different language called Lisp.
Yeah, the Lisp versus Prolog debate.
And these weren't polite academic disagreements either. There were fierce, almost nationalistic debates over which language was superior.
Because it was a debate about the very nature of intelligence, really, and how to digitally model it. The American approach with Lisp was highly functional and flexible, focusing on list processing.
Right.
But the European approach with Prolog was basically betting the entire house on formal logic as the singular foundation of artificial intelligence.
To make this tangible for you listening, think about it like cooking. Traditional procedural programming, which is what most of the software world still uses today with languages like C, Python, or Java, is like giving a chef a hyper-specific, step-by-step recipe.
Down to the exact measurements.
Right. Take 2 eggs, crack them into a bowl, whisk for 10 seconds, turn the stove to medium. You are micromanaging the entire process. Prolog, being a declarative language, operates on a completely different paradigm.
It's a totally different mindset.
It is like walking into the kitchen and just describing the perfect omelet to the chef. An omelet is made of eggs, it is fluffy, it is cooked.
Yep.
You define the parameters of the truth, and then you leave the kitchen. The chef figures out how to make it happen.
That analogy perfectly captures the shifting control flow. You are defining the relationships and the end goal, not the mechanics of the execution. And if we connect this to the bigger picture, this idea was so revolutionary at the time that it sparked some massive, incredibly ambitious technological gambles.
Oh, like the Japanese project.
Exactly. The most famous one, heavily detailed in our sources, was the Japanese fifth-generation computer systems project, the FGCS. This launched in the early 1980s.
And they went all in.
They essentially bet the future of their entire computing industry on logic programming. They didn't just write software, they built their entire operating system on a variant of Prolog called kernel language.
And their goal for this hardware was just staggering. I mean, they were aiming for up to 1 billion logical inferences per second,
Hmm?
a GLPS.
Right, a GLPS. And keep in mind the technological baseline of that era. In 1982, standard computers were operating at around like 10,000 to 100,000 logical inferences per second.
So they were trying to jump light years ahead.
The Japanese project was attempting to scale that metric up by orders of magnitude. And they weren't just writing better code to achieve this. They were literally hardwiring Prolog's unique execution model into the physical silicon architecture of the machines.
Designing physical hardware specifically to process logical deductions is such a wild leap. It makes me wonder how this logic engine actually works under the hood.
It's actually surprisingly elegant.
Yeah, the sources break down the mechanics, and it starts with a really simple foundation.
Mm,
In Prolog, everything is based on a single data type called the term.
great.
A term can be an atom, which is just a simple lowercase name like red or apple.
Mhm.
It can be a number. It can be a variable, which acts as a capitalized placeholder like X or person.
Or it can be a compound term, which nests these things together to show relationships.
Exactly.
Those terms are the building blocks. And a Prolog program itself doesn't look like normal code. There are no loops, no print statements, no step-by-step functions.
None of the usual stuff.
Right. It is really just a database of facts and rules. A fact is a simple, unconditional assertion of truth. So you could write a fact into the system that simply says Socrates is human.
Just a bold, undeniable statement loaded right into the database.
Exactly. Then you introduce rules. A rule dictates that a certain conclusion is true only if a specific set of other facts are true.
Okay.
Using our previous example, you could write a rule, all humans are mortal. Translated into Prolog's syntax, you were essentially telling the machine X is mortal, IFX is human.
So the machine now has a database of universal truths and conditional rules. And the user interacts with this by submitting a query.
Right. You ask it a question.
You ask the computer, like, is Socrates mortal? The sources mention the engine attempts to prove this by finding a refutation of the negated query using a method called SLD resolution.
Which is a mouthful.
Yeah, let me try to translate that jargon because it sounds like a legal defense strategy or something. From what I gather, the computer basically assumes your query is false and then searches through its database of facts to find a contradiction.
That's spot on.
It is like a detective proving a suspect is guilty by proving their alibi is physically impossible.
That is an excellent way to conceptualize SLD resolution. Prolog assumes Socrates is not mortal. It then looks at the rule X is mortal if X is human.
Okay.
It looks at the fact Socrates is human. It realizes the assumption that Socrates is not mortal creates a logical contradiction. Therefore, the original query must be true.
So it proves it by exhausting the alternative. But wait, if I just give the computer a massive sprawling pile of thousands of facts and rules and it just blindly searches for contradictions to answer my query, what happens when it goes down the wrong path?
Now we're getting to the catch.
Right. If I ask a highly complex question with dozens of variables, mathematically, that sounds like a nightmare for processing power. Surely, in the real world, that relentless searching would just bring a computer to its knees from the sheer volume of possibilities.
You've identified the core mechanical challenge of the language. This leads directly to Prolog's defining execution strategy, which is called chronological backtracking.
Chronological backtracking.
Yes, the system doesn't guess randomly. It explores the options systematically, mapping out a massive decision tree. Imagine navigating a really complex maze.
Okay, so if I am the Prolog engine in this maze, and I hit an intersection with 3 possible paths, I create a choice point.
Exactly.
I decide to take the left path, binding my variables to the facts down that corridor. But let's say I hit a dead end. The facts don't support the rule. Instead of crashing or throwing an error, the engine just stops.
It stops and then it backtracks. It undoes every single variable binding it made since that last intersection.
Wow.
It literally walks backward through the maze to the previous choice point and then tries the middle path. If that fails, it backtracks again and tries the right path.
That's relentless.
It searches this massive tree of possibilities, dynamically moving backwards and forwards until it either constructs a flawless logical proof or exhausts every single conceivable option and returns a definitive false.
So it will stubbornly try every combination until it finds the truth. Conceptually, that sounds beautiful. It is pure, relentless logic.
It is.
But computationally, backtracking sounds incredibly heavy. Which brings us to the biggest historical criticisms of Prolog outlined in our sources and the somewhat controversial compromises programmers had to make to get it to function in the real world.
Yeah, the purity of the logic engine came with a severe cost. Because it relied on this exhaustive search method, software developed in Prolog historically suffered a massive performance penalty compared to conventional procedural languages like C.
Because C just runs straight down the compiled instructions, while Prolog is busy wandering through a maze, checking every single branch and dead end.
Precisely. If you are executing a deterministic computation, meaning there is only one correct path to the answer, and you don't need the machine to explore multiple alternatives, Prolog's built-in backtracking mechanism is a colossal waste of computing resources.
It's doing too much work.
Way too much. It spends time setting up choice points and preparing to backtrack for scenarios that will never actually happen.
So if the backtracking is the bottleneck, I imagine programmers had to find a way to put blinders on the engine. They needed a mechanism to tell the system, hey, you found a good enough path, stop looking at the other doors.
They did, and they called it the cut.
The cut?
The cut is a specific operator, an exclamation point in the syntax, that a programmer manually inserts into the code. It explicitly commands the Prolog engine, once you make this choice, commit to this path. Do not backtrack past this point.
Wow.
Yeah, it forcibly introduces a deterministic path into a non-deterministic engine.
The irony there is thick. I mean, you come to a language like Prolog for the absolute purity of declarative logic. You just want to describe the problem to the chef and let them work.
Right.
But to make the program run fast enough so the computer doesn't freeze, you have to dirty your hands with procedural hacks. You have to step back into the kitchen and start micromanaging the search tree, manually locking doors in the maze.
It is a profound philosophical compromise. The sources explicitly note that relying on cuts destroys one of Prolog's main attractions, its purely declarative nature.
Because now you're giving it steps again.
Exactly. Once you start aggressively inserting cuts, you have to read the program procedurally to understand what it is doing. You have to trace the execution steps in your head rather than simply reading the logical truths.
That's a shame.
Furthermore, you lose the ability to run programs backwards and forwards, which is arguably one of the most magical properties of pure logic programming.
Let's expand on that magic, because the concept of running code backwards is entirely foreign to someone used to standard programming.
Oh, it's fascinating. In pure Prolog, a single logical relationship can be queried in multiple directions. Imagine you write a standard rule for concatenating or joining two lists together.
Okay.
In a procedural language, you give the function two lists, and it spits out the combined list. In pure Prolog, you can do that, but you can also do the reverse.
Wait, really?
Yeah. You can give the engine the combined list, leave the two input lists as blank variables, and ask the engine to find all the possible ways to split that large list back into two smaller ones.
That is amazing.
The exact same block of code computes both forwards and backwards. It just evaluates the logical relationship from different starting points. But the moment you add a procedural cut to optimize the performance, that bidirectional flexibility is permanently broken.
So you trade mathematical beauty for execution speed. And the sources point out this wasn't the only hurdle for the language. Building massive enterprise-level applications, what they call programming in the large, was incredibly difficult due to the severe module fragmentation.
Right. Yes. For a very long time, the creators of major Prolog compilers couldn't agree on a standardized module system.
And a module system is basically how you break a massive software program into smaller, manageable, isolated pieces that can talk to each other safely, right?
Correct. Without a standard, code written for one Prolog system often just wouldn't work on another.
Reading the timeline in our sources is almost comical. The ISO standard for the core Prolog language was published in 1995. But Part 2, which standardized the module system, didn't arrive until the year 2000.
It took forever.
And Part 3 of the ISO standard, which covers definite clause grammars, a crucial tool for parsing language, that was just published in June 2025.
I know, it's unbelievable.
It took the international community over 50 years to standardize that specific part of the language. Looking at the performance penalties, the procedural hacks, and a half-century of standardization delays, it begs the question, did Prolog just fail? Did the procedural languages like C and Java completely win the war?
Prolog didn't fail, it evolved to survive.
How so?
The academic and developer community recognized the severe processing bottlenecks associated with backtracking, and they developed brilliant algorithmic solutions. One of the most significant breakthroughs was a technique called tabling, which is a form of memoization.
Memoization, that's essentially the computer taking notes as it works, correct?
Exactly. It is a space-time trade-off. Systems like XSB and modern SWI Prolog implemented tabling to save the logic engine from endlessly repeating its own work.
Okay.
As Prolog evaluates a complex query and navigates the maze, it stores its intermediate findings in memory, in a literal table. If it wanders down a path and encounters the exact same subgoal it has already solved, it doesn't recalculate it, it just looks up the answer in the table.
So you sacrifice some memory space to drastically cut down the execution time. That sounds like a standard optimization, but how does it save the system from crashing?
Because it solves the fatal flaw of infinite recursive loops. Imagine you are building a family tree application in Prolog, and you ask the engine to find all of someone's ancestors.
Yeah.
In a pure depth-first search, if the data has a circular loop, say, two distant cousins married, creating a loop in the lineage, the Prolog engine will get trapped in that circle. It'll just keep backtracking and stepping forward infinitely until the computer runs out of memory and crashes.
Oh, I see.
Tabling breaks the loop. The engine checks the table, sees it has already evaluated that specific person, realizes it is in a cycle, and forces the search down a different path. It makes the language vastly more robust for complex, messy reasoning tasks.
Tabling saves it from endless loops. And that ability to handle massive, complex webs of logic without crashing is exactly why Prolog didn't die out, but instead became a secret weapon for modern tech giants.
It definitely found its specific uses.
Right. Despite the academic debates and the reliance on cuts, Prolog found incredibly specific, high-stakes niches where traditional procedural languages completely stumbled. Let's look at where this 1970s logic engine is hiding in plain sight today.
Prolog's unique architecture makes it perfectly suited for domains that require complex rule evaluation, namely exponent systems, theorem proving, and natural language processing.
The most prominent example in our sources is IBM Watson. When Watson went on the game show Jeopardy and systematically crushed the human champions, Prolog was functioning as a critical component of its cognitive architecture.
The developers at IBM needed a language capable of expressing highly complex pattern-matching rules over natural language parse trees.
And to break down why a parse tree is basically a logic puzzle, think of a sentence like, "The quick brown fox." Procedural code struggles to understand the contextual relationship between those arbitrary words.
Just too rigid for that.
Exactly. But if you mathematically map that sentence into a tree of grammatical rules, where a noun definitively connects to an adjective which modifies a verb, suddenly messy human language becomes a strict logic equation.
And Prolog was specifically designed to instantly hunt through massive trees of logical rules.
Right. That meant it could parse Jeopardy clues, identify the subject, and evaluate the grammatical relationships faster than any other language IBM experimented with.
What's fascinating here is the IBM engineers explicitly stated that Prolog was the ideal choice due to its simplicity and expressiveness for that exact task. It allowed them to write clean, declarative rules for English grammar rather than thousands of lines of procedural code trying to anticipate every possible sentence structure.
That's incredible.
But it isn't solely utilized by supercomputers. We see it in modern open source infrastructure as well. Consider Terminus DB.
Oh, right.
It's an open source graph database designed for collaboratively building massive knowledge graphs. And the entire system is implemented in Prolog.
A knowledge graph is, at its core, a massive web of connected facts. It links people, places, concepts. It makes perfect sense. I mean, what better tool to query and navigate a sprawling database of logical relations than a programming language built entirely around logical relations?
Exactly. It's the perfect fit.
Here's where it gets really interesting, though. Buried deep in the history section of our sources is my absolute favorite application. We've talked about IBM Watson parsing Jeopardy clues, but we also have to talk about Sega.
The video game company.
Yes. In 1986, Sega released the Sega AI computer exclusively for the Japanese market, and the operating system utilized Prolog.
They utilized it specifically for reading Japanese natural language inputs via a specialized touchpad.
It is wild to trace that lineage. A theoretical language born in the university in France in 1972, built entirely on the philosophy of formal logic, ends up parsing Japanese language inputs on a Sega console in the 1980s, and then helps an IBM supercomputer win Jeopardy decades later. It really underscores the deep versatility of the language.
It highlights a fundamental truth about computer science, really. Prolog is Turing complete.
Meaning what, exactly?
That means anything you can compute with C, Java, or Python, you can technically compute with Prolog. It simply approaches the computation from a completely different paradigm. It views computation as a sequence of logical state transitions, navigating a landscape of truths rather than a linear sequence of hardware instructions.
It fundamentally shifts how you approach a problem. And that brings us to the end of our sources today. Wrapping up this deep dive, it's clear that Prolog isn't just a relic of the AI Cold War, nor is it just an academic curiosity.
Far from it.
It is a living testament to the idea that sometimes the best way to solve an incredibly complex problem isn't to meticulously tell the computer how to do every little thing. Sometimes the most powerful approach is to just teach the machine what is true, step out of the way, and let it find the path through the maze itself.
For you listening, engaging with the concepts behind a language like Prolog, even if you never write a single line of code, expands your critical thinking. It trains you to separate the definition of a problem from the execution of its solution. In our modern, highly procedural world where we are constantly focused on the steps to achieve something, focusing purely on the truth of the system is a rare and valuable perspective.
It rewires your brain to look at the destination before plotting the steps.
It does. And analyzing this history leaves us with a lingering question about the future. We discussed how the Japanese fifth-generation project failed in the 1980s because they tried to build physical hardware specifically optimized for Prolog's logic, and standard general-purpose chips eventually outpaced them.
Right, the general-purpose chips won out.
But today, the computing demands of modern AI are hitting physical limits. Researchers are now developing neuromorphic chips hardware that physically mimics the synapses of a biological brain rather than relying on binary math. This raises a fascinating possibility. As we hit the ceiling of general-purpose chips, could the future of artificial intelligence be a return to that 1980s dream? Could the next major leap in AI involve taking Prolog's philosophy of pure declarative logic and hardwiring it directly into these new artificial digital brains?
Hardwiring a digital brain not to calculate math, but to instantly deduce truth. Taking the ultimate declarative language and fusing it with neuromorphic hardware. That is a completely new frontier to consider. Thank you so much for joining us on this deep dive into the source material. Keep asking questions, keep looking beyond the procedural steps, and we'll catch you next time.